ISS Satellites and the Thermosphere. When I first started researching flat Earth theory, one of the first things I had to accept, if I was going to even think about the possibility, would be that NASA and all of the photographs or composites, as they are actually called, or in video, whatever you want to call it, from space is fake. And I mean, that's a giant leap you have to take to to accept something like this, or to even consider it. And so I started watching videos that people had produced showing that the ISS was a hoax, and that satellites were fake. A lot of people, there were videos showing that on spacewalks, when it looked like they were on space, people caught a bubble rising from an astronaut's helmet, or a guy with a scuba tank inside the ISS in a window, and just other things like that. And so I first started seeing that stuff, and it was pretty convincing. But at the same time, I thought, well, it's not definitive proof, because how do I know that this stuff hasn't been edited in to sway opinions, because there are people out there that believe the Earth is flat and they want everybody else to believe it too. So I remained skeptical, but I also was doing my own little experiments on Earth with binoculars and just seeing how far I could see over the horizon, and drawing distances in AutoCAD and doing calculations and finding that I was able to see things much farther away, and observing the sun, the moon, the stars, and things like that. And so my opinion started to sway a little bit, but I still was trying to prove it wrong. But I'll never forget the moment that everything clicked. And that was on a Friday night. I was just watching videos, doing my typical thing, just wondering, trying to prove these things wrong that I was seeing. And I don't remember what video it was, but the narrator in the video said, how are there satellites and a space station in the thermosphere layer of the atmosphere when the temperature gets up to 2,000 degrees Celsius? And that's when everything clicked. I remembered, oh wow, I remembered from astronomy, my professor talking about the temperature in the thermosphere. And I remember her taking a marker like this and holding it out, and held it in front of the class like this, and she said, the temperature in the thermosphere layer of the atmosphere is upwards of 2,000 degrees Celsius, or can get up to upwards of 2,000 degrees Celsius. But you can't actually measure the temperature, because the gas particles in the thermosphere are spread so far apart that there are not enough of the particles collide with the tip of the thermometer to make it show a hot temperature, because heat is actually kinetic energy. And a thermometer works by measuring basically the collisions, the energy being transferred to it, and that's why it shows you what the actual temperature of the liquid or the air or whatever is. And so I remember sitting in class and thinking to myself, well, how did they measure the temperature in the first place? How do we know it's 2,000 degrees Celsius if you can't measure it? And I thought about maybe thermal imaging or something, but still you have to be measuring that kinetic energy. So it didn't make sense to me. But at the time, I didn't put two and two together and realize that that's where the majority of LEO, which are low Earth orbit satellites, and the International Space Station and the Space Shuttle used to be. What they used to, or the Space Shuttle used to be, but everything else orbits the Earth. And so when that hit me, I said, wait a second, this can't be. And I thought about the thermometer. I really started to think about thermodynamics, and I had to take thermodynamics to get my engineering degree, and so I went and I pulled out my thermodynamics book. I actually kept all my books. I didn't know I'd be using them for something like this later in life, but I knew I wanted to have them for reference, and so I got my thermodynamics book out, and I went to the first law, because I remembered what the second law was, but I wanted to read them both again. So when you go and you read the first law of thermodynamics for this book, says, the first law of thermodynamics is simply an expression of the conservation of energy principle, and it asserts that energy is a thermodynamic property. And that's basically more complicating what I say, and what I just said, that heat is energy, kinetic energy. Okay? And the second law of thermodynamics asserts that energy has quality as well as quantity, and actual processes occur in the direction of decreasing quality of energy. And what that means in terms of heat is that heat, something that's hot heat will move to a colder area, because the energy in something that's hot is higher than the energy in something that is cold. So they give an example, and they say, for example, a cup of hot coffee left on a table eventually cools, but a cup of cool coffee in the same room never gets hot by itself. The high temperature of energy of the coffee is degraded. It's transformed into a less useful form at a lower temperature once it's transferred to the surrounding air. So they give a little picture, they show you a picture of this, and you can probably imagine a cup of coffee cooling down, but they show that if the cup of coffee is 70 degrees Celsius and the surrounding environment is 20 degrees Celsius, eventually the heat will dissipate from the coffee and become the same temperature as the room around it, or the area around it. I mean, this is common sense. Everyone knows this, that if you leave something out that's hot, soup or whatever, and you don't consume it in time, it's eventually just going to be room temperature, and it may not be as enjoyable. So keeping that in mind, hot goes to cold. Now, before I took thermodynamics, I actually knew this pretty well because my dad is a mechanical engineer, and he basically groomed me to be an engineer from birth because that's what he is and that's what he knows. And he told me hot goes to cold. He wanted me to know that. It was something he was adamant about. But the way I really learned it is whenever I would leave the back door open in the summertime, he was, Ryan, shut the back door. You're letting the heat in. But in the wintertime, it was, Brian, shut the back door. You're letting the heat out. He always said it right. He always said that the hot goes to the cold. And so that was always ingrained in my head. And then when I took thermodynamics, I actually found the class very interesting because it built off of that basic principle that hot goes to cold. So why this all clicked for me, and you may or may not agree with this, is that I don't understand how this heat is not being transferred to the International Space Station and all the satellites up there. Let's look at how the atmosphere is constructed, or the layers of our air exist above us. If you go to Google Images or Google Images, or just get on Google and type in layers of the atmosphere or temperature, you might find this chart. I found this one. I decided to print this one out because it was the most clear. They vary with elevations and where the delineation lines are, but I'm just going to use this one to explain this. Okay, so basically there's 5 layers of the atmosphere or of our air, and we are in the troposphere. You might remember this from general science in middle school or whenever you took something like that. And when you go up in elevation in the troposphere, the temperature decreases. If you go up in the mountains, it starts to get cool. You might have experienced this. I mean, it's very common knowledge that as you go up into the mountains, the temperature gets cooler. And that always seems kind of strange, right? Because you're getting closer to the sun. But there's reasons for it. I'm not going to get into that in this video. But the temperature gets colder and colder, down to around negative 50 degrees Celsius, at about 10 kilometers over here. And then you get into the stratosphere, and the temperature actually starts to increase a little bit, which I always found kind of strange that it goes back up, and up to about 50 kilometers. And then you get to the mesosphere, and then the temperature starts to decrease again as you get into the next layer, and it gets down to about minus 100 degrees Celsius, which is about 100 degrees less than the freezing point of water. And then when you cross into the thermosphere, though, the temperature starts to slightly increase from about 90 to 100 kilometers based on this chart, and then it rapidly increases. I mean, it shoots up over 20, 30 kilometers. I mean, from negative 50, negative 100 degrees up to about 500, 1500 per this chart. Some say 2000 degrees Celsius, some say 2500 degrees. There's all kinds of numbers out there, but everybody can agree that it's really, really hot. 2000 degrees Celsius is very hot. To take this into consideration, or to put it in perspective, I mean, the melting point of aluminum is 660 degrees Celsius, and satellites and the ISS are definitely going to have a lot of aluminum on them. They're also going to have a lot of plastic on them for circuitry, circuit boards and things like that, and plastic melts at around the boiling temperature of water, which is about 100 degrees Celsius. So keep that in mind. So you see the temperature keeps going up into the exosphere, and it keeps going up and up and up off the chart. And the exosphere is basically the last layer of the atmosphere where the gas thins out so much that eventually you get to a point where there's no more gas and you're in space. And this is what I was taught in astronomy, and this is the general idea. I don't know if I said it exactly right, but that's the accepted theory. Okay? So those are the layers of the atmosphere.